Welcome back, AP. 19.5, we have our last variable that pretty much connects all of the variables of delta H and delta S into one equation. We got a couple learning objectives that AP would like us to learn, so let's get started, okay? Can we explain in a physical or chemical process if something is thermodynamically favored by looking at delta G? Okay, now delta G is a new variable. We'll get to the name down here at the bottom. Gibbs free energy change, delta G, in a chemical process in which all the reactants and products are present in standard state. So not only standard state as in a pure substance, but also molarity. Okay, so we know standard state as 1 atm, 25 degrees Celsius, but now when it comes to concentration, we also want the reactants and products to be at 1 molarity, okay? So there is one other criteria that goes with delta G that delta H and S don't look at. The standard Gibbs free energy change for a physical or chemical process is what measures if something is thermodynamically favored. The whole point of delta G is it thermodynamically favored or not? Okay. Oops. All right. People think that spontaneous, because it starts with the S, has to do with entropy, and it has nothing to do with it. Okay. Remember, entropy is about disorder, movement. The whole point of delta G is if it tells if it's a thermodynamically favored or not. Now, this is AP talking to you. Historically, the term spontaneous has been used to describe a process, but AP would prefer that you use thermodynamically favored. Okay. So if something is less than 0, which means if delta G is negative, that's thermodynamically favored, okay? So yes, you can abbreviate thermodynamically favored as TF, okay? But it also is good to make sure you know how to spell it too. Common misunderstanding, associating spontaneous with thermodynamically favored or suddenly or without cause. Okay, spontaneous has nothing to do with delta S. There is something that delta S can help us with thermodynamically favored, but it is not what determines it. Okay, so please avoid using spontaneous, use thermodynamically favored. When delta G is less than 0, that is the process that we want. Okay. If standard Gibbs free energy for a physical or chemical process may also be determined if you have a standard Gibbs free energy for the formation, reactants, and products. Notice also same as delta H. So same as delta H and delta S at standard condition. Okay. Products minus reactants. Okay. Nothing too difficult about it. But like I said, let's beware of coefficients. Okay, so how is all these variables connected with each other? So we already know delta H, enthalpy, heat transfer. Did heat go in or did heat go out? Remember, delta H also equals Q if it's at constant pressure. Delta S, entropy. Do you have particle movement? Do you have disorder? The more disorder, the higher the entropy. And obviously, this is what we're looking for. We're looking for positive results because remember, the second law of thermodynamics said that entropy of the universe needs to always be increasing. We want positive numbers, okay? If delta S goes down, that means you're creating order, which means you're creating less movement. But make sure you don't say there's no movement because every state of matter has movement. Delta G, here's the new one, Gibbs free energy, obviously after a scientist named Mr. Gibbs. Is it thermodynamically favored or is it not? But is it thermodynamically favored in a certain direction? So when we're looking at A mix B and we do our delta G, products minus reactants, is it thermodynamically favored in this forward direction? Or do we have to flip the equation to get it to be thermodynamically favored? So remember the second law of thermodynamics for a spontaneous reaction, aka TF, Entropy of the universe is always increasing. So when we're calculating delta S, we do want a positive value, okay? If it becomes negative, it becomes negative, okay? So Gibbs free energy, the amount of energy that is free or available to be useful to do work, okay? The meaning of the reaction to be thermodynamically favored means that everything happens on its own. You did not have to do anything that can be used to do work on the surroundings. Everything is going into the system, okay? If a reaction is not thermodynamically favored, which means now our delta G will actually be greater than 0. That's not a good thing. We want delta G to be less than 0. Means that the surroundings actually had to do some work, okay? Which usually the surroundings is you. Did you have to use a Bunsen burner? Did you have to stir it? Did you have to apply some heat? What had to happen, okay? So you had to do something in order for the reaction to work, okay? Gives free energy for a chemical process. Standard state, not only 1 atm, 25 degrees Celsius room temperature, but also molarity for the reactants and products. AP Chem tip is them talking to you. Even though reaction may be slow, okay, which means you would have an activation energy that's very high, okay, remember chapter 14, it does not mean that it's thermodynamically unfavorable. Just because a reaction is favored, we cannot say if the reaction is very fast or slow. So if the activation energy is very high, the reaction will usually occur rather slowly, okay? So thermodynamically favored has nothing to do with speed, okay? We don't know if it's going fast or slow just by calculating delta G. So what is the correlation? The sign of delta G is very important when we are predicting if something is thermodynamically favored. Now, obviously, we already know we want it to be negative. We want it to be thermodynamically favored. So if that delta G is anything less than 0, usually it happens at very high temperature, which means we're looking at stuff above 298, okay? And we already know it's irreversible, which means the forward process only. So we're talking about not, oops, put it over here, not equilibrium, okay? If it does come up positive, which is not what we're looking for, okay, so that means our delta G value would be greater than 0. The forward process is not thermodynamically favored. So A makes B, and when we calculate delta G, it would be a positive value, okay? Usually occurs at very low temperatures. So something usually lower than 298 degrees, 298 Kelvin. How can we get it to be thermodynamically favored? Well, we usually have to flip the equation. If you flip the equation, you can get it to be negative. And then it's thermodynamically favored, so B makes A. And now my delta G is now thermodynamically favored. Keep this in mind. There's an example problem coming below that we're going to do something like this. So energy must be supplied from the surroundings in order to get the forward process to actually occur, which means that's why it's not thermodynamically favored. Not thermodynamically favored. What if it's actually 0? Okay, that means you're at equilibrium. Usually it's a phase change. So maybe you have like water going to a solid, going to a liquid at equilibrium. So remember, when you're at equilibrium, you have no temperature change, but you do have heat increasing, okay? So remember those chapter 11 phase change graphs. At equilibrium, temperature's not changing. Remember this graph that looked like this and you went doot, 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 okay? We're talking about that right there, okay? So neither the forward nor the reverse is favored because you're at equilibrium. So chapter 11 phase change graphs, okay? One way to calculate delta G, as we already know, products minus reactants, okay? But there's something very similar to delta G when it comes to delta G formation. It's just like delta H when it comes to standard state, elemental form. What do we remember about elemental form when it's delta H? all the values are 0. So our pure solid, a pure liquid, 1 atm, 1 molarity, we don't have to look up any of these values, okay? So you have to remember when you see like H2 as a gas, delta G is going to be 0. You see sodium as a solid, going to be 0, just like delta H, okay? So don't waste your time looking up values for these. Unlike delta S, all particles have movement, have motion, which means they all have values. All particles have a delta S value, okay? Whether it's a very high value or low value, that's what we have to determine. So products minus reactants, and we already know, let's be careful with not only states of matters, but beware of coefficients, okay? I don't think we need to beat this one too much to death, okay? But how can we correlate delta S with delta H to predict if something will be thermodynamically favored or not, okay? So we do have an equation, and it is on your equation sheet, okay? So that's a good thing. So if we have delta S and delta H, can we predict if something's thermodynamically favored by having these two values? So in some cases, it's necessary to consider enthalpy and entropy to determine if something is less than 0 for delta G. So like the freezing of water, the dissolving of sodium nitrate, these are examples of these phenomena. So if we know delta H and we know delta S, then we can use this equation, but notice something about temperature. It's an isothermal process. Well, you learned about that word in 19.2. Isothermal means constant temperature, okay? And notice these little degree signs. That means that this temperature, that means it's at standard state. We can also use this calculation when it's not standard state too. So delta G, delta H, T, delta S, if it's not standard state, okay, that just means that the temperature, that means the temperature is any temperature, but not 298, okay? Nothing hard about this. The units for G is also the same as how delta H was, okay? So delta G and H do a lot of correlation with each other. Just one has to do with heat, one's about thermodynamically favored. So let's do a little practice, okay? Get out those calculators. Let's see what you can do. First, we need to write a balanced equation for the formation of NO gas. So if I want to form NO gas from diatomic nitrogen and oxygen, okay? So I have my standard state, 298. I got my skeleton equation. Let's do a little quick balancing. I have a 2 and a 2, makes it simple. Just add a 2 right there, okay? So, is a reaction endothermic or exothermic? Well, down below, I put the values down below here. They were up here instead. If a reaction is endo or exo, that means you have to look at delta H, okay? Is delta H positive or negative? Well, down here at the bottom, my delta H value is positive. So that means since delta H is positive, it's endothermic. Short, sweet, to the point, okay? Does the entropy of the system have more disorder or less disorder? Well, if it has more disorder, your delta H or your delta S will be positive. If it's less disorder, it would be negative. And notice right here, my delta S is positive. So this means it creates more disorder. You could even say particle movement since delta S is positive, okay? These are not novels, ladies and gentlemen, just get to the point. So now that we have a balanced equation, we have Gibbs free energy to use delta H and delta S. Let's calculate delta G. So we're going to use our equation. Now I can't go products minus reactants because I don't have any values. So since I have H and S, I'm going to use this equation. So H, T, delta S, okay? Now, the next thing to beware at, okay? Delta G, and I'm going to put these notes up here, okay? Beware of also units. They're not all the same units. Delta G, kilojoules per mole. Delta H, kilojoules per mole. But what do we know about delta S? He is joules, moles times Kelvin. Because temperature is Kelvin, that's how they're going to cancel. So first thing is, get this delta S, convert to kilojoules, mole.K. So all you're doing is just moving a decimal 3 places, okay? So this right here first, this delta S, we're going to change this into kilojoules. And it doesn't have the moles on here. If AP wants the moles, then we'll put the moles. So kilojoules over Kelvin. So I'm going to go 1, 2, 3. So 0.0247. You keep the sig figs, you just move the decimal. So now that I got the kilojoules, I'm going to put my delta H, 180.7 kilojoules, minus standard state, 298 Kelvin. And then my delta S, now that we have it in the proper unit, because the laws of math say that you can't add and subtract unless they're the same units. Okay, so let's bust out this calculator. So I have my temperature in delta S. Let's do this part first. So right here, 298 times 0.0247. Okay, so 3 sig figs. Now I don't usually round, I just cut it. 7.36. If you want to round, you can, but in this case, you don't have to. My Kelvin will cancel, so I will get kilojoules, but I still have my 180.7 kilojoules. So my delta G, subtracting those two values, 180.7 minus 7.36. And I'm going to get a positive 173. With sig figs, I have 2 after the decimal versus 1, so my answer is only going to have 1 kilojoules, and that's how simple it is, okay? But the first thing is don't forget to convert your delta S from joules to kilojoules, okay? Last question before we do a different one. Is it thermodynamically favored? Well, our delta G is positive, so this is not thermodynamically favored since delta G is greater than 0. Okay, and that's it, ladies and gentlemen. Let's just do a couple more examples. Let's practice products minus reactants. I have a balanced equation, 2H2, and I have O2, and it gives me 2 waters as a liquid. I have all the values that I need. Notice I don't have delta H or S, so I'm going to actually do products minus reactants. I have elemental state. Well, he's gone. I have elemental state. He's gone, but I have water. So I'm going to take those 2 waters, that is negative 237.2. And remember, this is delta G, kilojoules per mole. Okay, so let's multiply that out. 2 times negative 237.2. Oops, I think my decimal moved. And then right here, proper sig figs, 474.4 kilojoules per mole. Now I have my equation. Okay. I have my delta G, the sum of my products. Well, my products are negative 474.4 minus the sum of my reactants. Well, I don't have anything on my reactant side, so this made this very simple. So in the end, this reaction is negative 474. So now the question comes, is it, box our answer, is it thermodynamically favored? And yes, thermodynamically favored since delta G is less than 0. Okay, easy peasy. What if we flip the equation? If we flip the equation, will it be thermodynamically favored? Okay, well, remember, just like with delta H, Hess's law. And there is an AP video, an AP daily that's coming in Unit 9. I believe it's called Coupled Reactions, where delta G and delta H correlate with each other. If you flip the equation, they change signs. So back in chapter 5.5, Hess's law, where we would take the equations and manipulate them to get them to be the overall mechanism. If you flip the equation, it's just a change of a sign. So if my equation got flipped and I already calculated delta G, that means my delta G is going to now be a positive 474. So by flipping this equation, no, not thermodynamically favored, since the delta G is positive. Okay, so in this case, it is thermodynamically favored since it's less than 0. And if AP asks you in the forward or reverse direction, in this case, it was in the forward direction. In this case, it's not thermodynamically favored in the reverse direction because it's positive. Okay, so remember, if you flip the sign for delta G and delta H, okay, flip of the equation, just a change of the sign. Okay, I'd like you to try one yourself. Number 3, you have your hydrogen peroxide, you have your water, and you have your oxygen. Calculate delta G, products minus reactants, and is it thermodynamically favored? If we do this right, we should get this answer in blue. And see you on the next one.